Bon dia and welcome to the first experimental control session of this conference. My name is Markus Janusz and I'm heading the controls group at the Paul Scherrer Institute in Switzerland. And co-sharing with me is my colleague Gifre Kuni from the Alba Synchrotron. So the session will be opened by our first speaker, John Sparger. John is a control system engineer working with the Integrated Control System Division at the European Spallation Source, ESS. There he is especially focused on the control systems for the Neutron instrument. The title of his talk is EPICS Architecture for Neutron Instrument Control at the European Spallation Source. So please, John.
Okay. Thanks for having me. Like they said, my name is John Sparger. I'm going to talk about the controls for the instruments at the ESS. So the ESS is an international project, and so these instruments are being developed across Europe by the ESS member countries. 22 instruments are planned for the ESS, 15 are funded right now, and 8 will be ready for users by 2023. So this is an aerial view of a rendering of what the ESS should look like, and in that top right corner you'll see the target building and the instrument hall. And this is what the construction site looked like in August, so you can see they've poured the foundation for the instrument hall, and on the right is a map of where all the instruments will be around the target, the long and short instruments. So for the controls, you can really split it into 4 parts at the ESS. There's a personnel safety system that's there to keep people from getting irradiated too much or from asphyxiating. There's a set of neutron instrument technologies. These are interfaces that are being designed to reduce the complexity of the controls. So motion control interfaces, chopper interfaces. There's an integrated control system, so this refers to the EPICS layer and all the hardware like the PLCs that are distributed amongst the instruments. And then there's the data management and software center. So this is the group responsible for the actual user control of the experiments and for gathering all the data for analysis and storage. So in this talk, most things are going to be focusing on the instrument control, the integrated control system. And I'll also often say ICS will or ICS does because ICS is also a division inside ESS. So ICS provides a lot of infrastructure to the controls architecture. One important contribution is the timing system. So since the ESS is a pulse source, it's important that we be able to synchronize components like choppers properly. And so we're using a timing system developed by Micro Research Finland, and we'll use that to synchronize the entire facility from the proton source to the instruments and data acquisition. ICS also provides the ESS EPICS environment. This is a build system for the EPICS modules at ESS, and it's designed to reduce the complexity of creating an EPICS module by doing things like project introspection and cross-compilation for lots of different architectures and EPICS-based versions. It also is supposed to simplify building IOCs, so specifying dependencies and loading those dependencies at runtime so you can switch module versions. We also use EEE as a deployment system for EPICS. So control computers at the ESS will network boot from an NFS file system which contains all of the EEE modules and EPICS-based versions. And this is linked with continuous integration with our Git repositories. So we have Jenkins builds for tagged releases, and those get deployed as numbered module releases in the EEE file system to be used by IOCs when they start up. To be used by control computers when they start up. We also have ways to model our controls configuration. So to do this, we use a tool called the Controls Configuration Database. And this lets us model high-level components like EPICS modules and the types of devices that they can control. And we can also do very low-level modeling of our system to say there's a specific computer with specific IOCs controlling these specific devices. Several tools that we have consume data from this database. One of those is ICALEPCS Factory, and this is how we configure and deploy IOCs. So we can load an IOC template from CCDB and then fill in the values and deploy this to the appropriate server through the EEE file system. So when a control computer boots, it can look in the EEE file system for a specific folder based on its host name and know which IOCs to start. We're also using several more mainstream EPICS utilities like the channel finder, which is a directory service for PVs. So when you combine this with the RecSync utilities, IOC databases can automatically upload a list of their PVs to the channel finder when they start up and communicate to allow the channel finder to determine when PVs are disconnected. This integrates well with other tools like Control System Studio to let you see which PVs are available. And also, you can attach extra data to the PVs, extra metadata. So we'll use this as a component in our plug-and-play environment for sample environment systems that I'll talk about a little later. We're also using the Archiver, the EPICS Archiver appliance, which I think a lot of people are familiar with. And it's a client, an EPICS client that's continuously recording the PVs that you've asked it to record, so you can look back later and see historical trends or values. Finally, we're using CS Studio. So this is a tool that I think also a lot of people know about that lets you create nice operator interfaces and interact with the Archiver. So at ESS, we're going to be using CS Studio OPIs for all of the expert engineering screens. So when an engineer needs to troubleshoot a very specific problem, they'll look at these CS Studio screens, but users will be looking at a higher level control software called Nikos. So as I mentioned, there's also a lot of effort to produce standard interfaces to reduce the complexity of the controls at ESS. There are lots of motion axes on ESS instruments for things like slit systems to control the beam shape and shutters, positioning systems, etc. So the motion group at ESS has developed this standard motion control unit and also a library of sort of standard actuators and other motion components. And so for most devices, we'll expose their motion control axes as generic individual axes through the EPICS layer. And then high-level control will be done in the user interface layer with Nikos. So these axes can be assembled into devices to be used more specifically. In some cases, we'll be moving control into lower levels. So when there's a machine protection issue or we need fast response times, those may move into the EPICS layer, into the PLC. As I mentioned, ESS is a pulse source, and so, we have choppers along many of the beam lines, and these are designed to allow people to select certain wavelengths of neutrons within the pulse. And these choppers are going to be moving some of them up to 400 hertz, so it's a big important challenge to synchronize those precisely. Another challenge is that there will be several different chopper manufacturers' devices present on the ESS beam lines. So to deal with this, the chopper group has developed the chopper integrated controller called the CHIC to abstract this chopper drive control. So the CHIC will interface with EPICS for slow controls to talk to the driver, but also the chopper drivers will have direct interfaces to the timing system being supplied by ICS to do phase control. So here's a diagram of the setup. And in the middle, you can see the chick connected to the chopper drive controller on the right, and then that's driving the chopper, which is the big gray disk. And you can see that the EPICS layer is connected to the chick, but also the timing system has a direct connection into the chopper drive controller, and what this will be used for is to select the phasing of the chopper, and that will be done by modifying the phase offsets inside the timing system using EPICS. And there's also a feedback directly back from the chopper into the timing system, which is this top dead center pulse, so we can monitor the timing of the chopper rotations to make sure the phase is correct. The detector group at ESS is also developing a standard interface, so a standard readout system for the detectors, and it's designed to be compatible with a range of analog front ends. And this system is responsible for analyzing the events and forming them and passing them on to DMSC so that they can be combined with metadata from the rest of the experiment. And these have a direct interface to the timing system as well. So here on the bottom, you can see sort of a box representing the detector readout system in total. And so events from the detectors will go through some front end and be basically transformed into pixel ID and a timestamp to be passed on. And so we'll do slow control of these of the data acquisition system through EPICS, but there will be a direct timing interface so that this timestamping can be accurate. Also, all the associated equipment like the power supplies and the gas for the detectors will be controlled separately through EPICS. There's also going to be a large pool of sample environment equipment. So this is equipment used to change the conditions the sample is under while it's in the beam. So things like changing the temperature or the pressure or the magnetic field. And so since this equipment is pooled, it will move from detector to detector. And we want to sort of enable plug and play where this equipment, when it moves into a new detector system and someone plugs it in, it will self-identify. So what we've planned to do is have a small mini computer associated with each piece of sample environment equipment, and when this computer is plugged into the instrument network, the Receiver library I talked about before will have the IOC controllers notify Channel Finder, and Channel Finder will notify the user control NICOS that a new device is present. There are also several different systems using PLCs all along the beamline. ICS is responsible for programming and supplying these PLCs for things like vacuum systems, the utilities like the cooling water and detector gases, etc. And so just as an overview, this is sort of all the different systems that are present on the beamline. All along the bottom are all these different individual components, and they're all linked together through our timing system and EPICS, which is supplied by ICS. And then in the top left corner, all of the sort of user space utilities and data acquisition are connected to that. And we're also doing a lot of prototyping at the ESS to make sure all these controls work. So there's a lot of complicated pieces that need to fit together, and we want to make sure that by the time we start commissioning instruments that the controls are in a really mature state. So we have this ESS Instrument Integration project where we've installed a lot of different equipment and try to get it to talk together within this architecture that we've described. So in this lab we have ICS hardware running the EEE environment and the timing system, channel finder, etc. We have motion control systems, chopper drives, we even have a mini chopper. We have sample environment equipment like temperature controllers, and we have DMSC servers to do data aggregation and run NICOS, and we have this detector readout system, and that's all been demonstrated. And we've also been working with V20 beamline at the Helmholtz Center in Berlin. And so the goal of this project is just to try and demonstrate these technologies in a facility with real users. So the DMSC has already deployed NICOS to this beamline, and ICS has already deployed the timing system and phased the choppers there. So I should mention that this beamline is used by ESS to develop ESS technologies like the chopper controls for wavelength frame multiplication, and these active users will help us troubleshoot the architecture. So I think I'm out of time, so I'll leave it there.
Thank you.